Okay, so we now know how to do the first derivative and the second derivative rules, and that will help us give a general sketch for the graph. We're going to look at this one example to see how we can put that all together to make one sketch, and then we're going to look at an example that involves asymptotes. So if we find the first derivative of this equation here, you're going to get x squared plus 2x minus 3, which we know factors down to x plus 3, x minus 1. And if we take the second derivative, you're going to get 2x plus 2, which when we factor out the 2, we're left with x plus 1 in the brackets. So as a result, this one is going to give us x is equal to negative 3, and this one here is going to give us positive 1. And this guy here is going to give us x is equal to negative 1. So I'll just fill out the table for you, and then we can fill in the increasing, decreasing sections and concave up, concave down. So I've set the table up to show the zeros for each of these. By all means, you can plug in all the lines all the way down. They don't really matter because negative 1 is not a 0 for your first derivative, and same thing here. So we can actually just test a value in each of these intervals rather than testing each one of the intervals. But having said that, ultimately, the first time we want to look at our y values, and our y values plug in negative 3, negative 1, and 1 to get the exact values for the points. So at negative 3 and 9, that would be one of your points. Negative 1 and 3.6 repeating will be another point, and negative 1.6 repeating. So those are the 3 points that are of interest. And we don't require anything to be put in the actual intervals because we're actually looking to see, in this case, whether this is a min or max, whether this is a min or max, and this is one of our inflection points. So then we test values. So if we look in this range here, we could plug in negative 4, and we'll see that we get a positive value. If I plug in a value in here, I say plug in negative 2, you're going to get a negative value. And like I said, this whole box should be the same. If you're a little worried, you can test a value in between here. So if you plug in 0, you'll also find you get a negative value. This whole box should match because this doesn't actually change the min to the max. 1 up to positive infinity, you should get a positive. So then we look at our second derivative, 2x plus 2, and again we plug in a value that falls into this entire range. And again, if you wish to, you can plug 1 in for each one, but it doesn't really matter. It does all the same thing. So if we plug in a value into this box, we're going to find that we're going to get a negative value through this whole entire region, which means that that whole entire region is going to be concave down. If we look at this entire region, we're going to get a positive value. So again, this whole value right through here, that entire interval. Now using this information, then we can draw a quick little sketch. So since we're just sketching it, I've just put onto the x and the y-axis the points of interest, mainly where the min-maxes are going to occur, the inflection points, and the other min-max. So if we put a point here at negative 3 and 9, at negative 1 and 3.6, and at negative 1 and negative 1.6. So what we know right now is that y value of 9 and the y value of negative 1.6 repeating, those are going to be our two min-max values. If we look at our table, we have increasing to decreasing, which means that we're going to have a relative max. Here we have decreasing to increasing, so we're going to have a relative minimum. So we're going to have something that's going to do that. We can also see that from negative infinity to the inflection point, it should be concave down. So to the point, we get a concave down shape. At this point here, we now switch to concave up. So there's our cubic that we've now roughly sketched based on analyzing the shape of the graph using increasing, decreasing intervals and concave up, concave down intervals, and identifying the mins and the maxes and the inflection points. So now let's take a look at one with the example with the asymptotes. So if we look at this equation here, and we can automatically see a couple of things about it. 1, we know we have a denominator here where we have a non-permissible that x cannot be equal to 2. We know that's going to be a vertical asymptote automatically. Now, what we also want to look at now is horizontal asymptotes. So, if we actually look at the entire equation and we take the limit as we approach positive and negative infinity. So this goes back to taking the limit as x is going to be approaching infinity. We'll look at the positive one first, of 2x plus 6 all over x minus 2. Now there was a technique in doing this because as we go to infinity we're going to get an infinity over infinity case. So there's a technique where we take each of the terms and divide it by the highest degree. So if we have the limit as x approaches infinity and go 2x divided by x plus 6 divided by x all over x minus 2 over x. We can see that these ones simplify down because the x's will cancel out, and same here. So you will end up having the limit as x approaches infinity of 2 plus 6 over x all over 1 minus 2 over x. And we talked about how the limit as x goes to infinity of 1 over x, as you go towards infinity, this whole thing becomes 0. So when we look at the individual parts, this becomes 2, this becomes 1, 6 over x becomes 0, and the negative 2 over x becomes 0. So then, as a result, we get 2. This is going to be our horizontal asymptote. So now, on our actual initial graph, automatically we now know we have a point here, a 2 that has a vertical asymptote, and in addition to that, we have a horizontal asymptote at 2. Now you want to look at your first derivative. So if we take the first derivative, we have the denominator, because we're using quotient rule, times by the derivative of the numerator, which is just going to be 2, subtract your 2x plus 6, multiplied by the derivative of the denominator, which is 1, all over x minus 2 all squared. When we simplify this down, we get 2x minus 4 minus 2x minus 6 all over x minus 2 all squared, which then gives us, cancels, negative 10 all over x minus 2 squared. Now for critical points, again, you still do want to look at the denominator. We have an x equals to 2 is a critical point. Happens also to be our vertical asymptote in this case. There's nothing else that will set this equation to be 0 because there's no x in the numerator. Now we're going to look at the second derivative. So again, take your denominator, x minus 2 all squared, multiply it by the derivative of the numerator, which is 0, so it will disappear. And then we subtract negative 10, our numerator, multiplied by the derivative of your denominator. Now, you can expand it out, or you can use the chain rule. So 2 will come out front of the x minus 2, and then multiply by this. X minus 2. Remember, you take the 2 up front, drop the degree by 1, and then you multiply it by the derivative of the inside, which happens to be 1 in this case. That whole thing is then going to be over x minus 2 squared all squared. So your second derivative, this part disappears. You now have positive 20 times x minus 2 all over x minus 2 to the 4th. There's a common factor, so you're going to get 20 all over x minus 2 cubed. Again, on the denominator, x equals 2, that's then a critical point, also identified here as well. And again, there's no x term in the numerator, so as a result, we don't have any other critical points to worry about. So now if we actually plug in some points and we look at whether it's increasing or decreasing. If you say plug in 0, which is less than 2, you can see that you're going to get a negative value over something that's being squared that's going to make it positive. Same thing here if you plug in 3, a negative value divided by something squared to make it positive. So you're actually going to get 2 negatives. If you plug in, again, for the second derivative, say 0 and 3, Same thing's going to happen. It's going to be positive this time because our numerator, well, I've made my numerator positive versus here I made my numerator negative, or you could have made your denominator negative on that one, doesn't matter. In this particular case, because you're cubing it, anything that ends up being negative down here will make the entire thing negative, which in this case, if I plug in 0, 0 minus 2, then you're going to get a negative cubed, the whole thing's going to be negative. Same thing here, if I plug in 3, 3 minus 2 is going to become positive. Anything that's positive cubed becomes positive, positive over positive, whole thing becomes positive. So that now tells me that it's going to be decreasing, decreasing through the whole graph. And it also tells me that it's going to be concave down versus concave up. So a rough sketch, and again we have no point values in this particular case because 2 is an asymptote. We will have an asymptote here at 2. We will also have another asymptote here at 2 because we took the limit. And now we have a graph that's going to be decreasing, decreasing, but it has to be concave down. So, I mean, it could have been decreasing up here, but then it's going to hit the asymptote. So it has to start below the asymptote. It also has to be concave down, which it is in this region. And we need to have one concave up. And again, if it started down here, you'd cross the asymptote, so that would not work. And it doesn't have a true min or max because it's a continuous decrease as you go down. Same thing here, it's a continuous decrease as you go through. There's no actual increase to get to a maximum to come back down. So it's constantly decreasing through the whole graph. It has the asymptote to guide them, and it has a concave down and a concave up section.